Alright, so in this video we're going to begin section 13.8, which is extreme values. So first let f be a function of x and y, then the point x naught y naught is a critical point of f if the partial of f with respect to x evaluated at x naught y naught equals the partial of f with respect to y evaluated at x naught y naught, which equals 0. So both of your partials are equal to 0. Or if f sub x at x naught y naught or f sub y at x naught y naught is undefined. So our definition of critical point with a function of two variables aligns with the definition of critical point with a function of one variable. So your derivatives here, your first partials are equal to 0, or your first partials at that point are undefined. And we're going to use critical points in a similar manner as the way we use them in Calculus 1. So relative maximum and minimum values and what are called saddle points only occur at critical points and if you look back at quadric surfaces, saddle points were actually, a saddle was actually introduced there, or saddle point. So you can see page 822, figure 13.15. The point 000 is a saddle point of the hyperbolic paraboloid, which is also just sometimes just called a saddle of the hyperbolic paraboloid. And I'll also do an example where we'll see a saddle point in the example as well. All right, so now how do we go about finding or determining whether a critical point is a relative max or min or a saddle point? We use what's called the second partials test. So second partials test. Suppose the second partials of f are continuous on a disk whose center is the critical point x naught y naught. Let d of x naught y naught be equal to the second partial of f with respect to x evaluated at x naught y naught times the second partial of f with respect to y evaluated at x naught y naught minus the mixed partial f sub xy at x naught y naught. That last term is squared. All right, so we're going to use this function d to determine if the critical point x naught y naught is a saddle point, a relative max or a relative min. So A, if d of x naught y naught is greater than 0 and f sub xx at x naught y naught is greater than 0, then f of x naught y naught is a relative minimum. And in doing this, so you may find multiple critical points, and you would take each one of those critical points and you plug them into this function. So if you end up with this scenario, you know that that particular critical point is a relative min. This f sub x at x naught y naught, if you want to, you can use f sub y. Either one of those will work to tell you if this is greater than 0. If that's greater than 0, of course, then this is greater than 0, or f sub y is greater than 0, then you have a relative min. Just use whichever of these is the easier function to deal with. So say, for instance, f sub xx ends up being 3x squared y times cosine of xy, whereas f sub y is just whatever, 4x. Then you would use f sub y because it's easier to plug points into that than it is f sub xx. So B, if d of x naught y naught is greater than 0 and f sub xx at x naught y naught is less than 0, then f of x naught y naught is a relative maximum. C, if d of x naught y naught is less than 0, then f of x naught y naught is a saddle point. Or actually, this one should say x naught comma y naught comma. So it should say, because I just gave you the z value, But when we say a saddle point, so when we say relative max or relative min, we can talk about the value as a relative max, the value as a relative min. When we say saddle point, I actually should be giving a point, not a z coordinate. So let's change this to x naught, comma, y naught, comma, f of x naught, y naught. So it's actually the point is a saddle point. Now, if you're asked where a relative min occurs, here you would say x naught, y naught. If you're asked where a relative max occurs, you could say x naught, y naught. Or if you get to the point, then you would give the x coordinate, the y coordinate, and this is the z coordinate. If you just ask for the value, you just give the z coordinate. So it just depends upon what you're being asked for. So the only scenario that we don't have here for d, so d is greater than d is greater than 0, excuse me, it's going to give you a relative min or a relative max. Either one of these, you can use f sub y if you want to. If d is less than 0, you don't need to consider f sub xx or f sub y at all. You know immediately that your point was a saddle point. And then if d is equal to 0, this test is inconclusive. So you can't get any information if you find out that d is equal to 0. So if d is equal to 0, or d of x naught, y naught equals 0, this test is inconclusive. All right, so but you're not likely to encounter that at all. You'll just be given problems where you're not going to get that your d of x naught, y naught is equal to 0. And if that does happen, then it's a problem where you can figure out if a max, a min, or a saddle occurs at x naught, y naught by inspection. That means you could compare that point to points around it, or you'd have some possibly a surface where you can easily tell. So if you have a paraboloid, for instance, and you got and x naught, y naught was, it says an upside down parabola, and this is the peak, but you got the d of x naught, y naught is equal to 0, then you can just compare that to x naught, y naught that is functional values to other functional values around it, or you can tell from the nature of the equation or function that you're given. But for the most part, you won't encounter d of x naught, y naught is equal to 0. All right, so now let's look at an example from your textbook. So we're on page 882. We're going to look at number 10, which says in exercises 1 through 23, find all critical points, determine whether each critical point yields a relative maximum value, a relative minimum value, or a saddle point. So they give us that our function is f of uv equals u cubed plus v cubed minus 6uv. All right, so the first step is to find our critical points. And finding your critical points means first you have to find your partials. So your first partial, so f sub u is going to be equal to 3u squared minus 6v. Then f sub v is 3v squared minus 6u. Now, critical points occur when both of these are equal to 0. So if you find a value, or you find values u and v that make this 0, but they don't make that 0, it doesn't satisfy being a critical point. It's a system of equations. They both have to simultaneously be equal to 0. It's not that one of them equals 0, and the other one does not. So we'll set both of them equal to 0, and then we'll solve the system of equations. So 3u squared minus 6v equals 0, and 3v squared minus 6u equals 0. Now we have a system of two equations with two unknowns, so we can use substitution. So I'm going to solve this one for v and substitute it into here. And you can go through the algebra however you want to, as long as you do it correctly. This section 13.8 and 13.9 are both very algebra intensive, so just be careful with your algebra. So I'm going to divide both sides by 3. That gives me u squared minus 2v equals 0, which gives me v equals negative u squared and then divided by negative 2. So u squared over 2. And I'm going to take this v and I'm going to substitute it in right there. When we do that, that gives us 3 times u to the 4th over 4 minus 6u equals 0. And I can factor out a 3u from both of these terms, which tells us 3u times u cubed over 4 minus 2 equals 0. So now that says 3u equals 0, which gives us u equals 0. Or u cubed over 4 equals 2, which is u cubed equals 8, which says that u equals 2. So now we have these two different u values. We're going to take each one of those and substitute them in there to get the corresponding v, because we should have a u and a v for each one of our points. So for u equals 0, so we're going to take these, we're going to substitute them back in here to solve for v. So for u equals 0, when I put it in there, I get v equals 0. So one of our critical points is 0, 0. And when u equals 2, we put that back in there and we get 2 squared is 4 over 2, which gives us 2. So when u is 2, v is also 2. So those are our critical points. All right, so now we want to determine whether we have a relative max, a relative min, a saddle point at each one of these critical points. So we need to set up our second partials test. So now we need to take our second partials of our functions up here. Be careful to make sure that you look at the correct function when you take each one of your second partials. So you need the second partial with respect to u. So I'm just using this right now. I'm going to take the partial of this with respect to u, and that's just going to give me 6u. And then f sub vv. So now we'll go over here and we use this. I'm going to take its partial with respect to v, and that's going to give us 6v. And then f sub uv or vu, it doesn't matter which one you do. So f sub uv is, I'm going to take the partial of this thing with respect to v, and I get negative 6. All right, so now we have our partials, and we can set up our function d. And we'll just write d for shorthand. Remember, your d is going to be f sub uu times f sub vv minus f sub uv squared, which for us, that is 6u times 6v. So we get 36 uv, and then minus this squared. So that's going to be minus 36 for us. All right, so now we're ready to take our critical points and plug them into this function to see what we get. So d of 0, 0, when we put that in, we just get 0 minus 36, so we get negative 36. So when we go back to the second partials test, if d is negative, so this is less than 0, we have a saddle point at 0, 0. And if we wanted to know what the z coordinate was, we would just take that and put 0, 0 back into our original function. So then d of 2 comma 2 equals, so 36 times 4 minus 36, and we just care if is that negative or positive, and that's greater than 0. So as soon as that's greater than 0, we take our point and we need to plug it back into either f sub uu or f sub vv. It doesn't matter. I tend to always use the first variable, so in this scenario uu or xx. So f sub uu evaluated at 2, 2 is going to give us 6 times 2, which gives us 12, which is greater than 0. So remember, it's kind of counterintuitive, same for the second derivative test from calculus 1. So this is greater than 0, tells us that 2, 2 is a relative min. So we have a relative min at 2, 2. All right, so that completes that problem. But wow, since we got one saddle point, I just quickly sketched kind of an intuitive image of what you get when you have a saddle point, and then we'll stop this video here. So if you imagine you have whatever, some hilly or mountainous region, and say for instance we have so somebody's walking whatever up this hill, so our little stick figure is walking up that hill, and we also have, and this hill, we'll say that this is going, so this is kind of like at a 45-degree angle in the XY plane. And then say we have, for instance, the hill that goes, or you could say that one's actually like going, we'll draw another one, say like this. And both of them are going through the origin. So it's like some region is, this person is walking up the hill. For them, that's a peak, whereas the person that's walking along this way, for them, that's a valley. So this point right here will be called a saddle point. So this person, this little stick figure here, the hill that this person is walking along, they're going down to a minimum, whereas this person is walking along the hill and they're coming up to a maximum, but they're the exact same point that they're approaching. So that will be considered a saddle point, which is what we had here at 0, 0. All right, so I'll stop this video here, and then in the next video we'll do some more 13.8 examples, and I'll introduce a couple more topics from 13.8 as well.